So, dear all, I have to present you our new lecturer, Jürgen Lisenfeld. He is an expert in design, fabrication, and measurement of qubits. He comes to our summer school from Karlsruhe Institute of Technology. Thank you.
Thank you. Yeah, hello, everyone, and welcome to this last lecture of today, last lecture of the week. I'm going to give you an overview and talk about quantum systems, but these are quantum systems which we actually don't really want to have. They're like parasitic quantum systems, things that disturb us. And especially we're looking at materials which have some disorder. And this allows actually some of the atoms in this material to be delocalized between two positions in space. And this is actually one of the biggest problems we have if we want to build a quantum computer. You know, there is some effort to make a superconducting solid-state quantum processor. And we could already do it if you wouldn't have these parasitic two-level systems, these parasitic quantum systems. Yeah, so I already said, called them two-level systems, TLS. This is the topic of this lecture. And it turns out that they affect really a large variety of different devices, especially quantum devices and high-precision devices. So it may be just a rather big challenge which we have in technology. So especially also these two-level systems, they disturb a lot the coherence of superconducting quantum bits. As you can see one example here. And the reason is just that these individual atoms like this delocalized atom likes to tunnel strongly to such a large microscopic quantum bit. And so my research is actually focused on kind of turning this metal around. We just will use the qubit to exploit the strong interaction to learn more about the properties of these TLS. So we study their physics using the qubit as a microscope, as a detector of image. Okay. Yeah, a short introduction to myself. Well, I'm basically from Germany, so I did my diploma in Erlangen. This is close to Nuremberg. Then since 2008 or so, I'm in Karlsruhe, basically just a postdoc. I'm still just a postdoc. And the topic of my PhD thesis back in Erlangen was just to demonstrate a superconducting qubit, and I somehow managed, after a few years of struggling, to show the first coherent oscillations in a superconducting quantum computer. And since that, I'm basically just in Karlsruhe as a postdoc, surviving from third-party funding. Here, the Deutsche Forschungsgesellschaft and especially Google are very helpful because they just provide my salary. And otherwise, I'm pretty sure I could not survive in German university landscape because there's simply no permanent positions for guys who just want to do the research. Here you can see a picture of Karlsruhe. So this is the castle in the center. And the university campus is just this one here. The KIT is a big technological university which is famous for engineering. For example, Carl Benz developed the first cars there. So it's a pretty nice university and a pretty nice town. So make sure that if you come to Karlsruhe, visit by. I'm just sitting here in this tower. This is a physics building, physics tower, where all the physicists are constrained. Okay, so just feel free to interrupt me anytime if you have some questions, some complaints. It's always good to have some discussion, of course. So the outline of this lecture, so the general plan of this lecture is, first of all, to give you a bit of a break. I understand that you had exhausting 2 weeks already with many complicated lectures, and there were already topics such as symmetry break-in and quantum chaos. So here my goal is just to give you a nice relaxing overview of the field, give you just an inside view of an experimental point of view and not bothering you with too many equations. So the first lecture today, I'll just talk about the basics of these two-level systems, how we can measure them and what kind of devices they affect. And then, some topic also already is about superconductivity. Then we will talk about superconducting resonators, like this thing here, which already allows us to get a pretty good overview of what we seem to have here in these materials. The rest of the lecture then will be mostly about superconducting quantum bits. So you will hear about how they are made, how they are operated, what you need for this, and what kind of problems you will find. So basically we talk about decoherence due to these atomic tunneling systems. Yeah, and depending on the time and how it goes, then I'll just finish the lecture with some fancy experiments people are doing to understand this better and to maybe circumvent these problems. Okay, so yeah, let's start about materials. Turns out there's actually boring and interesting materials. On the left side, you can see both sides basically silicon oxide. Oops, silicon oxide. So here, however, it's crystalline modification. So you know, every atom in the crystal has a nicely defined position and an energetic minimum, and everything is nicely ordered. However, you can also find silicon oxide in its amorphous form where you don't have this order. So there's not anymore this regular ring shapes. For example, you find here smaller rings and larger rings, and not always these hexagons like in the crystalline version. Now you can of course argue, well, this crystalline version has some beauty to it, it's very symmetric, but on another point of view it's also kind of boring because it's completely understood. You can just calculate the thermal properties of this material by thinking cleverly and starting from first principles, which is not possible for the amorphous materials. And for example, already, so in physics this also makes the amorphous material of course a very interesting material and especially puzzle. There's many things that are still not understood. For example, already the question arises, are we sure that this is actually the reasonable picture of this amorphous materials? It's not so easy to figure out because our typical way to find out something about crystal structures is of course to do X-ray diffraction. So here we have the constructive interference from these planes of atoms here, and we can just calculate this back to the status constant, and so this is obviously not possible here because there is no order there. You will not get any X-ray contrast in this materials. So the first question is, is this epiphany of Eliason, who we had like 100 years ago, actually true? And since recently people actually managed to look inside these amorphous materials using scanning tunneling microscopy. For this, however, it's necessary to make a rather flat amorphous material. So this is actually just a 3-atom thick layer of silicon oxide floating on a beryllium surface. And this allows you to do microscopy images. This is one of these results. You can see both versions, both the crystalline version, where you have nicely these hexagons when you focus on the silicon layer, or the oxygen. And everything is just, of course, as predicted from crystal theory. However, in the amorphous material, you can actually now see that we have these different ring sizes here, which is just pretty similar to what has been seen by the inner eye of the Eliason. And in principle, it's, to make this two modifications, you can just cool them down quickly. Then you get a glass, you freeze in the glassy state, or you cool it down very slowly, kind of you anneal the sample to the crystalline version, and then you get this higher order. Also it's possible now, since you have these nice two flat amorphous films, to not only make pictures but also make movies. And this is actually now a transmission electron microscopy movie of this amorphous film, and I'm just going to play it. Here it is. Okay, so now the movie plays. It's only a few seconds. Actually, the real time was like 10 seconds or so. But you see, of course, when you start the movie, everything moves a little bit. There's noise, obviously, there. But you can also see some interesting things. For example, if you focus on this region here, then you will see that you start off with a like two larger rings opposing two narrow rings. And now if you let time evolve, then suddenly something occurs and there's some rotation between the atoms happening. And now you have this more crystalline version of the material in this small space here. So kind of the material crystallizes a little bit just by providing some noise or some tunneling. And also here there's a lot of this going on. So what I want to tell is actually that this amorphous material offers room for dynamics. So you can have moving atoms in the amorphous material, but not in the crystal, because in the crystal, of course, everything is already in the lowest energy state, and it's pretty difficult to actually get the atoms out of there. So, and this is already the central problem that we are going to discuss. If you have something that can move, it will move, and if it moves, then it generates noise and dissipation. Okay, so the story about the amorphous materials starts like 40 years ago, when people actually got their hands on dilution refrigerators. So first it was possible to cool something down to below 100 millikelvin, for which you use this dilution refrigerator. And then of course people started to cool down materials, and look what happens. In a very simple experiment, you can just take, for example, a piece of glass or a piece of crystal, cool it, connect it to a cryostat, and on the one side you can connect a heater and just apply some energy there and see how warm it gets on the other side. This allows you to measure the specific heat, for example, or you can also measure the heat transport through this material. So people did this, and if you do this with a crystal, then you will basically find a curve like this. This is now the thermal conductivity as a function of the sample temperature. And the data points here are lying exactly on this curve, which was predicted by Jürgen. So this is basically just, again, showing how that everything is understood in the crystal. I mean, we can completely predict these properties here by basically here evoking the phonon density of states, which take, of course, the role of this heat transport. So this is well understood and rather boring. If you do the same on a glass, so you can just take a microscope slide here and do the same experiment, and then you will find a strikingly different curve. So you'll see that for the amorphous form of the same material, we have here completely different temperature scaling of the conductivity, and also there's this interesting plateau here at intermediate temperatures. Yeah, and this was very surprising to the people. I mean, they were really trying to understand this. And moreover, they found one more surprising thing. It doesn't really actually matter what kind of material you take. So you can take any material which is amorphous and actually even find a quantitatively identical properties at low temperatures here, below, let's say, 10 Kelvin. And these are really very different materials. Yeah? I mean, this is biatomic glasses here. Everything with a P here is a polymer, so polyethylene, PET, or PMMA, which is also a famously used material for nanofabrication because it's photoresist or acrylic glass. So as long as it's amorphous, it will have this dependence. And this is, of course, a big question. I mean, why is this so? And there's more than the thermal conductivity. Also, people noticed that there's a strange response to electric fields. So AC electric fields, for example, if you transmit some microwaves to this material, you'll see that the loss actually is reduced when you put more of these energies through. And another very kind of smoking gun for what happens here is this measurement, which is the specific heat as a function of temperature. So the specific heat, of course, tells you how much energy you need to warm a certain mass of this material up by a certain temperature. And you will see that the specific heat of this amorphous material is much higher at low temperatures than for the crystalline version. So this means that you can put some heat here, but it will not end up in the phonons which you are measuring with the temperature, with your thermometer. So basically, the energy which you have put inside there has to be somewhere else in the phonons. And this leads to the conclusion that you basically see that glasses must contain intrinsic states which are able to absorb this energy which we apply here, which prohibits it to dissipate into the phonons. Okay, so then basically after these thoughts, it was soon possible to develop a basic theory about these two level systems, which is the famous standard tunneling model. Basically at the same time proposed by Phillips and by these three gentlemen. So the idea is, you already know, glasses must contain some intrinsic states. And since you already had this idea about the structure, then of course, well, not too far-fetched idea is that, okay, this could be just some of these atoms which are able to somehow go into a higher energy state, or to basically be excited to a different position where they may have higher energy. Yeah, and these are just now these famous TLS, these tunneling systems, because actually this motion between these two positions occurs at low temperature, which means it cannot be a thermally activated effect, it must be a quantum effect. And so we can describe this by such a double potential. We have two minima here, which already indicates we have two positions which are possible. And since it's quantum mechanical, it must be quantum mechanical, we describe by a wave function, which is actually kind of delocalized between two parts. In other words, you can imagine that this atom tunnels here at a certain tunnel rate between these two positions. This potential is also characterized by some asymmetry energy, so telling you which of these two states is preferred. This asymmetry energy is shown here. And yeah, these two things basically you just enter into your Hamiltonian. You have the tunneling rate here, taking the state, and the energy bias basically defining which law is preferred. Now you can imagine if you have such an atom which tunnels, the atom is likely to carry some charge, because some of the charges, of course, also contain the bonding. So basically, if you have tunneling charge here, you will have electric dipole moment. So the electric dipole moment is just this charge times distance, and accordingly, you would expect that such a thing would respond to the electric field which you apply. And you can just imagine it applies a these electric field in the material, which allows you to drag this particle to one side or the other side, and accordingly you change the asymmetry energy. Likewise, obviously the strain in the material should also play a role, because if you apply strain, we make these atoms move a little bit, maybe change the density, the local density, and this always, of course, will very much change the local potentials at the position of this TLS. So we expect that these TLS couple the strain into electric field, and accordingly, by some reasonable thoughts, you can come up with the conclusion that this tunneling rate here is basically constant, but only this asymmetry energy here will depend on external parameters, which is now the electric field here, happening to the dipole moment of the TLS, and likewise the mechanical strain, which couples to another constant, which is called the deformation potential. Yeah, and now if you would do this, if you would now apply some DC field or some strain, you should see that the energy difference of the TLS states, actually this one here, this is the wrong sign, sorry, this is delta E, this depends then on this hyperbolic function on the asymmetry energy. So for symmetric dipole potential, you will see that we have the minimum possible excitation energy of the TLS, just given by the delta naught or delta tunneling energy. Yeah.
Delta and delta zero the same?
I'm sorry?
Delta and delta zero.
Yeah, sorry. Yeah, this is, I started some confusion actually with this, the symbols, because classically all these guys are using delta naught for the tunneling energy and delta for the asymmetry energy. But I was always confused with what is delta naught, and then of course you have certain indices, and then it was just a mess. And I just adopted the flux qubit notation, and you use rather this asymmetry energy epsilon rather than delta. Yeah, so if you, probably I also confuse you, if you look into the classical theory or classical papers, just understand that this is typically called delta naught, and this is called epsilon. Thanks for the question, yeah, this is another fault. Okay, yeah, so then basically the key point of the standard tunneling model was to predict some properties, and here people started to think about the distribution of these parameters. So you know that if you're tunneling, something always depends exponentially on the integral through this barrier here. So this is like this function. Now you can just assume that these kind of tunneling parameters here, like the distance or the tunnel barrier heights, will be equally distributed. So basically, everything is possible here. And likewise, you can then come up with the density of states for the TLS. So you can predict. No, you can predict actually that the distribution of this TLS below 1 Kelvin should be constant, which means that it doesn't matter at which energy you look, you have the same probability to find all of these TLS. They are like completely spread out flat over the frequency band up to some maximum energy, which is about 10 Kelvin. Yeah, and this is of course a very central prediction because this allows us to now verify our measurements. We know, for example, in specific heat, we just need to know what kind of, how many systems you can excite there as a function of temperature, and then you get basically this linear temperature dependence as I showed before. Yeah, these are just some typical values. The density of states, so this constant density here, is about, I like to use this value here, 1000 TLS per gigahertz and micrometer cube. This is just a convenient energy density with often in similar quantum bits because well, we have small things and we work at microwave frequencies. The electric dipole moment is typically 1 electron angstrom. So basically, one electron can move about 1 angstrom to 10 meters, which is of course the typical distance you will find in such a material. And the coupling to strain is rather strong. This is this deformation potential here, by which the TLS couples is applied to strain field. And it's 1 electron volt, which is very large, considering that we are here working basically at 1 Kelvin temperature, so you rather have like milli-electron volts of energies or below. So we have a two-state quantum system. So this means you can excite it, or it can be excited, but it can also decay back to the ground state. And it turns out that since this coupling to the phonons of the TLS is so strong, the relaxation rate of a TLS is mostly or completely given by the strain coupling. So this is a relaxation rate from the exact state back to the ground state. You know it's always proportional to the square of some coupling element, the coupling matrix element, or some coupling strength. So you'll put here the square of this coupling to strain, the phonon coupling strength. This is just the phonon velocity in the longitudinal and transversal phonons. And you also see some temperature dependence here. So the point I want to make is that this, of course, this relaxation gives rise to dissipation. And you have now two possible dissipation mechanisms: the mechanical loss, which generates some internal friction, which you can express as some loss rate or some inverse quality factor of a resonator, for example. And you see it's just again proportional to the density of states, this constant here, this universal constant actually, and strain coupling and some density here of the materials and some velocities. So by the electric dipole moment P, the TLS can also couple to fields and generate similar dielectric loss. Here we often talk about the loss tangent, tangent delta, which is again some kind of inverse quality factor if you wish. This is then just again proportional to the density of TLS and the permittivity of the material. Yeah.
What should I imagine on the internal friction?
Internal friction. Well, basically, This is actually a good question why it's called internal friction. Maybe I should call it mechanical loss. I mean, friction is of course something which generates loss, mechanical loss. I'm not sure actually why this is called internal here. Anybody has an idea? Okay. Sorry, maybe it's just a confusing word which I read somewhere without probably thinking what it actually means. Maybe it just means that this mechanism for this friction is inside the material. Yeah? So you don't have like friction when you move two things against each other. The material itself, by these intrinsic defects, generates friction under deformation. No, I tried. Okay. Yeah, this relaxation has some nice, interesting effects. For example, you will see that the specific heat of your amorphous material depends actually on the time. So this means that you can apply heat pulses of different length. So you just shortly pulse your heater on the material for maybe 1 microsecond here, or for longer. And you see that actually you don't see much specific heat when you use very short pulses. Only when the pulse length is comparable to this relaxation rate, then you will see that the defects have now enough time to respond to these phonons which you applied there. And this is, of course, also a very unexpected effect which you don't find in regular crystals, regular materials. The other thing is that it's actually difficult to cool down these materials, these amorphous materials. People recognize that after they started the cryostat, it can take rather a long time until the sample really equilibrated and got cold. And this is again just the effect of this relaxation rates, which I have to say also are widely distributed. I mean, each TLS is different, right? You have a large disorder, large random environment for each defect, and that's why each defect may have a different coupling to strain and accordingly different relaxation rate. There's fast ones and slow ones, and the slowest ones here, which have the weakest coupling to strain of 4 months, those will be the ones which give this long logarithmic tail of your energy relaxation rate. Yeah, these are another typical values. If you look at TLS in superconducting quantum circuits, which will be the topic of the next lecture, then then basically you will find that the TLS don't live so much as long, maybe up to 1 microsecond. If you take a bulk glass, then it can these TLS have a much slower relaxation rate, which also gives some indication that well, in the bulk, basically, you have the TLS better isolated from effects like the surface, like interface effects. And of course, the superconducting qubits, as you will see, basically are thin films which are pretty much affected by some surface contributions. And that, of course, means that if there's more degrees of freedom to couple to, this relaxation will just be enhanced. So this standard tunneling model was quite successful to already explain a lot of the basic properties of these amorphous materials, like specific heat you could predict. However, there's also a few things which you can still not predict today, and definitely not on the basis of this tunneling model. Because one thing which is missing is the interactions between these TLS. I mean, you know, TLS now has a double moment, so if you have two next to each other, they could of course just talk to each other via double interaction, or by coupling, by exchanging a phonon, for example. And this also was observed pretty early in the experiments. And what people did here to observe this is basically used again a piece of glass and sent one ultrasound pulse through and measured the attenuation of this ultrasound pulse. You can do this, but before you do this, you can also send a very strong ultrasound pulse at a very specific frequency, in a very sharp frequency band. So this means that by this very strong pulse, you excite TLS at exactly this frequency here, to the excited state, or actually to the saturated state, meaning they are 50% excited, 50% in the ground state. And once you did this, you can then just probe, okay, now what happens? Using a second probing pulse of much weaker power. So you don't excite the TLS with this probing pulse, but you can see which of them are excited. And so you'll see this is the response which you measure sometime after you applied this strong saturation pulse. And you see it's much wider here in the frequency compared to this very sharp ultrasound pulse which you started with. And in fact, also people can measure that the width of this so-called hole in the attenuation increases with time. So the obvious conclusion is that, okay, TLS cannot be stable in frequency, they must diffuse in the frequency. Like it's indicated here. If you take some TLS, you can just do like a random walk and its frequency will just drift up and down. And yeah, this was already, as I said, observed, and the explanation for this effect is actually that the effects interact. And now it's important to know that there's kind of two different types of defects. There's defects which have a high enough energy above the thermal energy. So these you can call coherent TLS or real quantum systems. But there can also be similar TLS at lower energy. They can be of the same physical origin, also tiny atoms, for example, but just by chance have a very small tunnel barrier to overcome. So that's why they would actually have such a low energy that they are thermally activated over the barrier. And so this then you have to treat as a classical two-state system, a classical fluctuator if you wish. You also call them often thermal fluctuators. And you can imagine that this would just randomly change its states. And now if you have these interactions between these two types of defects, then of course it can happen that this changing of the state of this TLS changes locally the field or strain at the position of the neighboring TLS, at this high frequency defect, and then you change its symmetry energy by this change in the field, and this then will change its frequency. And this is actually the origin of these spectral diffusion, of these frequency drifts of these TLS. It's driven by the thermal activation of these low energy thermal fluctuators, TLS. Yeah, and this actually is one of the also generates big problems when we want to build quantum systems which are free of thermal noise, because even at low temperatures, you will still find very small energy fluctuators here, which can then still kind of transfuse these fluctuations into a higher frequency band, leading to some change of the spectrum of these high frequency defects, which of course then can affect the properties of your quantum device. So yeah, there's more open questions or more problems with this standard tunneling model. Basically, it's still not understood where this plateau comes from. There's a variety of theories, but not really defined a clue. And also this universality here. I mean, why do all these materials behave similarly, even quantitatively? And for example, Anthony Leggett was often expressing his wonder about this fact, and he didn't really believe that this is just by chance. So yeah, there's still many open questions in the material. Of course, people still today work hard on the tunneling models to improve it. And there's a few refined models nowadays, and actually every few weeks another idea can come up with which takes a new approach to explain this. Just to give you a broad overview, I'm not going to talk about these models here, also because I'm sure that Lara Faoro on next Monday, who will talk about the theory of these TLS, will cover those in all the detail you need. But just to give some general ideas, of course you can assume that maybe this TLS is made up from a large number of atoms, and in a large number of atoms you can of course have like local excitations or really more specific things, such as for example oscillations of these boundaries here, which then could contribute some kind of bosonic energy scale. And another approach is to actually just assume, okay, maybe we just have two different types of defects. This is a two TLS model here. The generalized tunneling model, actually by Faoro and Joffe, this takes into account specifically this interaction between defects and can predict now something like the noise in the resonator, for example. Or you just assume a certain shape of the downward potential, maybe not this just similar one, maybe one which has a certain form, such that at higher energies you get also some harmonic contribution. These are all tries to somehow get into account or explain these plateaus here at intermediate temperatures. Yeah, and finally also some people try to bring phonons into the game. I mean, the TLS would be somehow pressed by the phonons surrounding that, and this then can, for example, modify the TLS density of states. So you would not expect any more constant density of state, but rather something which may have some special feature here that could explain these plateaus. So there's also limitations of experiments. Since maybe 20 years ago or so, people could not measure TLS individually. So you were just relying on these bulk experiments using really a piece of glass, a bulk thing, and just then you of course measure only the response of this large and inhomogeneous ensemble of TLS. Yeah, each TLS is different, so you just get a kind of joint averaged answer, and this of course makes it very difficult to predict how the individual defect actually behaves. Yeah, and at the end, since you had only these bulk measurements and experiments to verify your theory was also just forced to basically predict distributions of parameters in order to come up with the resulting thermal properties. Yeah, this actually will change in the next lecture. Certainly you will see that we can now look into individual defects by actually exploiting the strong interaction between the qubit and the individual TLS. And this of course changes a bit the game, and hopefully will bring us new insights how these defects actually are formed. Okay. So let's talk a little bit about possible devices which are affected by these TLS defects. Well, I told you There's an ominous thing called internal friction. Actually, you can see this in resonators. So for example, if you take such a nano guitar here, which has some strings that can vibrate, then obviously when the thing vibrates, the mechanical strain in this material would just periodically change. And this means that the double potentials of the TLS would just also periodically change a little bit. And then of course you can get transitions from the sides of the higher well to the lower well by emitting one phonon. And this is of course the incoherent phonon, so you dissipate the energy into the phonon path. You can actually exploit this to learn something about the effects. And one famous device people used here are these so-called double pedal resonators. So you basically etch out of silicon, out of crystalline silicon, this interesting structure here, and then you excite it using just some asymmetric fields at the resonance frequency. The oscillating mode which you have in this structure is actually shown here. So you have these kind of arms here which would do like this, and you have this head here which would do like this, actually, like this. I think. Yeah. Okay, so you can imagine this is some oscillation, and the advantage of using this mode is actually that most of the strain is just confined here in the neck of this resonator. And this just means that you have not so much losses due to the clamping, due to the fixture of this resonator. Okay, so what you typically then do is you make this thing here, you just put it down first to measure what quality factor it has, or what friction it has by itself. And then you can just coat this neck here with your material on the test, which could be some more silicon oxide film or whatever you would like to test there. And then you measure again the loss, and you see higher loss, and the difference, of course, then must somehow be only due to this additional material which you put here into this highly strained region. Yeah, and this has been, of course, done a lot, and is still done a lot today, to basically figure out whether we can, for example, make amorphous materials which have not so much of these TLS. Here's, for example, one example of such a measurement in such a double pedal resonator. So basically, you see that this is our mechanical loss rate, or the inverse mechanical quality factor, is a function of temperature. And you can see that this is actually all the same materials here, but just differently fabricated. You can deposit this material here with some beam evaporation. So you just heat some metal with an electron beam, and it evaporates and condenses there. Or you can sputter it. And you see already this makes a big difference in the mechanical loss. Here it's also interesting to see that when you expose this material to hydrogen, which are the lower curves here, then the loss is significantly reduced. And here the idea is actually that with the hydrogen you can separate dangling electronic bonds, which exist in the amorphous materials due to the large disorder. And this not only limits this lengthening of this bond, but also it constrains the material further. So you have a higher density of this material, which just restricts the motion of these atoms more compared to the unsaturated material. Yeah, and so these kinds of insights you can get with these resonators. So there's also a very large device which is pretty much limited by the TLS, and this is LIGO. You know, LIGO is this large Lisenfeld interferometer which has a 4 km long wavelength, and it's used to basically detect gravitational waves just by seeing the anisotropic deformations of the space when the gravitational wave moves by. And it was nice to hear actually that despite this impressive precision of this LIGO device, what at the end limits your fidelity is really this TLS. And in this case, the TLS are found on the mirrors of which are at the end of this interferometer. And this is actually normal that you have this amorphous material here. You typically use it as an optical coating to enhance the reflectivity. And on the other hand, this actually means that since you have this mechanical noise by these motions of the TLS inside, this will actually also generate some effective noise, which turns out, as they have here in this paper, is the utmost limitation of this LIGO. And this is somewhat really surprising because, you know, every kind of possible trick has been played to bring this device to its absolute limit, which is also necessary to find these gravitational waves, and TLS also here one problem. So many quantum devices are of course affected by this TLS. One example are ion traps. So the classical version of an ion trap is this Paul trap here, where basically you are able to align some atoms here on a string in the middle of these electrodes. And you do this in the following way. If you look at the cross section here, you will see that two opposing electrodes are put on the same electrical potential, and the others are basically on the other polarity of that. So you just connect those using an RF source, so high frequency source. And you can imagine that when you have now the situation of this ion is there and you have a negative polarity here, then if the positive ion will be just able to move along this direction, but will be confined in this direction. And what you do then is to avoid that this particle moves in this direction or escapes in this direction, you just, after a short time, invert the polarity, and then the particle is pushed back here to the center point, but now able to move in this direction. So this at the end means that you effectively generate such a rotating saddle potential for the ion, which should sit here on the saddle point. This thing is rotating, so basically keeping it in the center. And actually, there's a nice anecdote how Paul invented this trap. The story goes like this: that he, at some Sunday morning, wanted to bring his wife some breakfast while she was still lying in bed. And the breakfast was consisting of, one hard-boiled egg, apparently, which he carried on a plate. And then he basically had this egg on a plate, and he just walked there, and of course the egg wants to roll away from the plate, but he noticed that once he rotates this plate at a certain frequency, which somehow matches the mechanical properties of this egg, then he was able to stabilize this egg in the center. Yeah, and that's how he got his Nobel Prize. Always be nice to hear, right? Yeah, here's some versions of these actual traps. This is a bit outdated trap of Los Alamos. Here you see these electrodes here, and also some ions here. So these ions you can really see just by using a CCD camera. To see this, actually use a laser to excite these ions here to some state which has an optical transition. And ideally also short lifetime, so you can collect many photons when you induce this transition here with the laser. So basically see the fluorescence of these atoms here, by which you can not only find its positions and count them, you can also, of course, probe their quantum states. Because obviously this laser will not be resonant to this transition if this ion here is already in this excited state here. So this works basically to read out this quantum state of these ions. This is also a nice picture I like very much. It's basically a PhD student trapping some ions in the group of Chris and Monroe at the University of Maryland. And I like it because it really shows that top science is not made by old gray-haired professors and lab coats. It's rather done by motivated young students in dark labs and long nights, not even having proper clothing. So yeah, I just like it. So. Yeah, and basically you can see that here you see the CCD camera image of the ion cloud, and here you see the AC of the RF field to rotate the subtle potential. And I suppose that she's trying to change here the amplitude or the frequency of this field in order to condense this now into a nice string of ions. Yeah, then of course you have the optical table here using the lasers and the camera, and yeah, basically all kinds of RF electronics. There's also a more modern version of ion traps, which is basically the flat version. So you can make a trap actually in a two-dimensional way by basically mapping these electrodes here to these flat arrangement of DC and RF electrodes. And you'll still be able then to trap an ion above these electrodes here by probably adjusting these frequencies and amplitudes. And now you could try to make a quantum computer out of these individual ions. So basically by having this chip, putting some atoms inside, and then since you are able to also move these ions using some corresponding potentials to push them around, you can actually move these ions here freely around the chip. And for example, you could move them into the field of a laser, where you can then do quantum operations, or you can just move them somewhere so that they are stored. And this is one way how you could maybe put a scalable ion-trapped quantum computer, because in the classical version, using such a linear trap, you are limited to the maximum number of ions that you can put there. Maybe 50 or so, but then at some point it gets too complicated, also because the longer this chain will be, the more foreign modes you have inside there, which you have to cool. So that's why it's an advantage to use small packets here, which is just easier for cooling, and in principle this will be a scalable version. And this has also been done. So this is one example of a so-called atom chip. So you make here such traps here on a chip here. And actually in this way you see that you can also make some kind of circular racetrack. So this is, the ions can be stored here in the center. These green things are all the trapping electrodes. And then it's possible to move the ions here in a circle as you wish, and move them here also in 2 packets inside some laser beam. So you can do 2 qubit operations here, or single qubit operations. And this in principle should allow you to make a scalable quantum computer. However, of course, you have TLS on the electrodes of these trapping electrodes, so on the surface of the trapping electrodes, because basically all metals that we are using tend to generate some amorphous metal oxide when we expose them to atmosphere. And so you can expect that you have basically a film of TLS always on these surfaces of these electrodes here, which then of course generate electric field noise. So the thermal fluctuations, for example, even low temperature, can then just locally generate fluctuations of the E field, which of course then makes noise, which is called excess heating in the case of ion traps. And you can see the heating rate of this of such a system here really depends on temperature. Here, as expected, you remove the phonons, everything cools down well. After some point where you see the TLS now hit in, and they generate here this excess heating, basically this excess noise in the ion traps. So there's another version how people try to make solid-state quantum computers. This is so-called quantum dots, or semiconductor quantum dots. Here you can just make a stack of semiconductors which have different doping, like gallium arsenide, or indium gallium arsenide, or aluminum gallium arsenide. And now you can dope this upper layer here, and at the end, these electrons that you put here, they will diffuse to this layer here. This interface layer between these 2 semiconductors, simply because here the energy, the potential energy of these electrons would be the minimum, so they like to stay there. And this is of course just an interface, so a very flat thing, and at the end this allows you to generate a 2-dimensional electron gas here at this semiconductor interface. So you have not so much electrons here, depends on your doping of course, but the electrons can very easily move. So then the idea is, okay, if you have such a 2-dimensional electron gas, you could try to confine it to one point. And an easy way to do this is just by using electrostatic fields to kind of expel these charges here from some area under the state. So by putting the voltage here, you can now basically generate a certain confined area, confined dot for these electrons to sit, which are called quantum dots. And you know, if you have like a fixed potential, like something which confines the wave function of the electron, you have of course discrete states in this, which you can then use for quantum computation. This is an example of such a quantum dot, so-called double quantum dot, because there's 2 positions where you can put an electron. So you put, for example, positive voltages here, and then an electron can sit here or there. By this potential of this electron, you can kind of change the tunnel barrier between these 2 positions here. And in principle, then this is already a qubit. You can encode it by the position of the electron, either here 0 or there 1, or you can also use the spin of this electron. And then, of course, also can put like 2 electrons in the same double dot and just use the spin degree of freedom. Yeah, this is in principle a nice approach. However, despite now, I don't know, 20 years of research, people are still struggling with coherence there. And the reason is again just TLS. So again, we have metal electrodes here. We will have a TLS on the oxides of this metal electrode, which generate electric field noise. And Here the problem really is that we have a very short distance between this electrode and the TLS and the electron here. So even single TLS can affect a lot the local potentials here, which of course generates then decoherence. Okay, yeah, this brings me actually to the end of this first chapter. And now we go into superconductivity. So now let's see what can we do with superconducting electronics to figure out what TLS actually are. So a few words, general words about superconducting resonators. So we have an electrical system. Of course, you can then model it as an RC resonator. So you can imagine a capacitor here carrying some charge. The charge can move through some inductor by generating some magnetic field to the other side. And so this charge will just oscillate back and forth, and the energy will be always converted between charging energy and inductive energy. So if you take a classical, well, if you take any resonator actually, it will not oscillate forever because there's dissipations. For example, in the dielectrics of this capacitor here. And this just means that the amplitude of your oscillation will decay with a certain time constant. And this allows you to define a quality factor, which in fact is really just the number of oscillations that you get here during kind of this half-lifetime decay of this amplitude here. So this is just the definition of this quality factor. Yeah, and so then basically, if you make such experiments, you have to consider that you also have to couple this LC resonator to some excitation device or some AC electric field, for example. So typically, you just connect another capacitor here to put some AC there, and then we have two mechanisms of loss. You can have the internal loss of this resonator, maybe due to this losses here in the capacitor or in the inductor. And also you will have some loss to the coupling of your excitation device. And this is basically called the coupling Q factor. This is the internal Q factor, and you have to add all these loss rates, the inverse quality factors, to get the final Q factor. Yeah, and as I already mentioned or indicated, the superconducting resonators, so we can basically be sure that we don't expect much loss from this inductor here because it's superconducting. But we will need some dielectric in this capacitor. And for example, if you make a capacitor using aluminum oxide, you will find a loss rate times delta of 10 to minus 3. So basically the Q factor will be about 1,000. Get 1,000 oscillations before the energy is dissipated. And you see that other materials can have lower loss. For example, silicon nitride has a little bit smaller loss. And of course, the crystalline aluminum oxide, the quartz version, has the least loss. Yeah, these are examples of real devices made on thin films using superconducting metals like aluminium or niobium. And you just fabricate them on a substrate like silicon or sapphire. And in one version, you can just make here the inductor from a long and thin wire here, and the capacitor from this kind of interdigitated capacitor. Yeah? So you just have small distance between these fingers here, providing some capacitance. And then, of course, you can excite it by coupling it to some transmission line. I will show in a minute what this actually is. Or you can make an overlap capacitor where you have two plates separated by the diameter. Yeah, so transmission lines actually we use on chips. I mean, you want to have a silicon chip where you can put some high frequencies, microwaves, for example. And for this, you need some kind of coax cable. Because you need some waveguide, which has a defined impedance to make the wave travel. And this is now the version of a kind of a flat coax cable. So like in a conventional coax cable, you have some interconductor and some outer shield, the ground. And here you just map this to a two-dimensional structure. You have here the inner conductor carrying the signal, and there's some gap here, and it's surrounded by the ground plates. Yeah, like a flat coax cable. Now to make a resonator, out of this you can just define the length of this coax cable using some coupling capacitors here, some gaps in the film, and then excite it, for example, here with some AC. And then you would see that some standing wave can be formed here when you hit the resonance frequency of this device. The resonance frequency will be given by the length of this inner part here. As of course you know from anyone ever has seen a guitar, for example. So there's two versions. You can have the same boundary conditions on both sides, and you get a half wavelength resonator, basically having such a resonance frequency here. And there can, of course, also be multiple harmonics of this resonance frequencies in this transmission line resonator. You typically don't get harmonics in a lumped element resonator, but here you do. Yeah, and here you see, for example, the voltage profile of the second mode, having maximized the voltage at this end here, and of course the current would be maximum here at the nodes. Yeah, or you just short one end and you have a lambda border resonator, and then of course you get different resonance frequencies, as you very well know from basic physics. This is an example of such a superconducting resonator. Here you see again this superconducting film here structured into this common waveguide. Here's a transmission line. And now to measure such a device, you just apply some frequency in the vicinity of the resonance frequency here on one side, send it to this microwave line here, and see how much comes back here. So if you look at the amplitude, which is basically transmitted here, you see at the resonance frequency you get this dip here, so the window of the transmitted energy, because actually the resonator kind of absorbs, it stores the energy in its resonance frequency, which is why you get this minimum at the resonance frequency. Resonators always also show a phase shift when you move to the resonance frequency. So you can also measure this using a network, vector network analyzer, and basically you get typically this step here by 2 pi in the phase. Simply because if you drive slowly, some mechanical resonator will oscillate in phase. If you drive faster and faster, it will actually show this anti-phase oscillation. Yeah, this is the so-called network analyzer, a standard device to measure these transmissions of microwaves in this case. So you very simple thing, you send microwaves at different frequencies here, and it measures how much comes back here. These two parts are connected to these 2 points here, and this is a typical result of the function of the frequency here, plotted with an amplitude plotted versus frequency. So you see here already these 3 sharp dips, which are just 3 different resonators which were coupled over the same transmission line. Yeah, and then of course you use these measurements here to fit these curves to extract the quality factors. So this basically is just given by the width, by the broadness of the resonance curve related to the frequency. And yeah, typically for these microwave resonators here, we make them from aluminium, so you can have like several hundred thousands up to maybe a few millions. I think Sergei Krylov already told you a bit about fabrication of these nanocircuits, so I can also make this short, I guess. You just use this substrate here, typically silicon or sapphire, aluminum oxide in crystalline form. And it's then actually good to put first here after you clean the substrate some metal film, some superconducting metal by evaporation typically. So you use some vacuum chamber here and use, for example, E-beam evaporation to condense the metal here on the substrate. Then you can coat this with a photoresist. And here you use just this photoresist spinner. This is actually a small turntable which can rotate at several thousands RPM. And you then, once it's rotating, or before it's rotating maybe, just put a drop of photoresist on the center of this chip, then spin it up, and then the centrifugal force will spread out this photoresist very homogeneously, which also defines then the thickness of the film. Simply you change it by changing the rotation. Yeah, again, of course, then once you have this photoresist on top, you have to develop it, expose it to some light, either E-beam or UV light, and this means that you break the polymer bonds in this photoresist. It makes it weaker. At this point, then you can wash it away and basically develop it. So we have here now basically the metal exposed only at certain parts, so you can just expose it to some etchant, maybe even just some acid in the beaker, and remove this metal here. And afterwards, you put everything to acetone to remove this photoresist, and you're left with your structure. Yeah, to measure these things, one important thing is to shield your system from the external noise. And we're dealing with superconducting electronics, so we will work at very small temperatures, about 20, 10, 30 millikelvin. So this thing is at 30 millikelvin, and this is actually at 300 Kelvin. This is our network analyzer. And we have to make sure that the thermal photons, the thermal noise here in this room temperature electronics does not reach the sample. What you do here is you use attenuators at different temperature stages. For example, here you have one at the 4K state of the cryostat, which then already a lot reduces the noise power which you get from this hotter attenuator here. But since you know that each resistor also generates a noise itself, due to the fluctuation dissipation theory, each resistor also generates noise corresponding to its temperature and its resistance. You have to further down this higher temperature stage noise here by having further attenuations at different temperature stages. Also, you need typically to use some band pass filters to make sure that only the frequencies which you're really interested in are able to reach your sample. And also isolators are often used, which allow basically to travel a microwave only in one direction, not in the other direction, like a diode if you wish. And one interesting thing is also that people a few years ago noticed that they have another noise source, which is actually infrared photons. You know, superconductors are sensitive to light. I mean, the pairing energy of these group pairs is like microelectron volt. Several microelectron volts. So definitely much less than the energy of an infrared photon. And it turns out that people had actually a lot of infrared photons in their sample stage here because the coax cables which they use typically use Teflon dielectric, which is nice because it has small loss, but it's transparent to infrared. So actually people figured out that the light from the room temperature goes just through these thin coax cables all the way through these filters and so to the sample and actually breaks the superconductivity by generating quasi-particles. Yeah, and then the solution is of course just to put some infrared filter there. You can see one of our versions here. This is just another piece of coax cable. We have replaced this Teflon dielectric with just some dark epoxy, with some black epoxy to shield this. Okay, yeah, this is actually this is the thing I used for my PhD thesis. It's an outdated version of a cryostat.
Sorry.
Yeah.
In this context of infrared heat,
Yeah.
I mean, could you comment? Are you sure that it's 30 millikelvin or is something else?
Yeah. Well, the thermometer actually installed on the cryostat can show 10 millikelvin, for example. Yeah. But actually, we are often talking more about the electron temperature of the sample. So basically, the charges, the electrons in the metals may have a higher temperature than actually your thermometer shows. For example, by being generated, for example, by these infrared photons, which are not directly coupled to the phonons, but rather deposit the energy in the electron path. So, yeah, this is actually also one of the key experiments which you typically do. You try to measure the temperature of your cuboid versus the cryostat temperature. You typically see some saturation there. So the sample is typically higher at higher temperature than 10 millikelvin. So maybe 80 millikelvin is not a too bad value that you can get there if you are sure that everything is nicely shielded. And you're right, if you have not these infrared filters, your sample temperature here will not be the base temperature. Okay. Yeah, this is just a picture of our lab, of the Ustinov group in Karlsruhe. It's also a little bit outdated. What you need to measure these things then is basically some microwave sources here, maybe some pulse generators if you want to make short pulses of microwaves, and of course a cryostat. And this is our old version of a cryostat which still uses liquid helium, which you have to fill up every second day. Requires some 30 liters of helium to keep everything cool. Well, this is actually the picture of the lab which I'm working in today. So now we're using, of course, mostly these cryogen-free dilution refrigerators, which don't need the liquid helium supply. You can see here some network analyzers, microwave sources, some electronics, the computer to control everything, and of course to provide some music.
Sorry,
Yeah.
just a quick question. What about this mechanical noise and the difference between using liquid helium compared to like a compressor?
This is a good question, and I will actually come to that. Yes, the pulse tube, I will explain the pulse tube cooler, and then you will actually understand what's going on here. Right, this is a state-of-the-art dilution refrigerator, which is actually used by Google to now try to build a quantum computer. So if you use, as you will understand in the next lecture, if you have superconducting quantum computers, you need two signals, typically one magnetic flux to tune the qubit and one microwave to excite the qubit and make quantum operations. So basically, this is why all these cryostats have a large number of cables, coax cables here. As I said, basically 1 or 2 for each current. And then you can see that it can become a bit bulky when you really want to scale up to 100 qubits or so. So yeah, this is already some kind of technical challenge which we are facing here. But of course, there's solutions. For example, people can also use flat coax cables, not really these three-dimensional coax cables. But on the other hand, this is something which you cannot really avoid if you want to really scale up big quantum processes. Yeah, so this is actually now the sketch of a pulse tube cooler. So basically, for a delusional refrigerator, you first need to come to something at 4 Kelvin. If you are below 4 Kelvin, you can use this delusional refrigerator principle that you can basically mix two quantum liquids, which is helium-4 and helium-3. So there's a mixing chamber. You have helium-3 in the top and helium-4 on the bottom. And these two different liquids don't want to mix, actually. However, you can use some quantum effect. Well, due to tunneling actually of this helium-3 into the helium-4 phase, you can absorb energy. And yeah, I don't want to go into detail. At the end, this allows you to cool it. But first, you need to have to go to 4 Kelvin. And for this, we used further informatimes liquid helium, and now use these pulse tubes. And the pulse tube is basically just like a Stirling cooler. So, you know, a typical refrigerator just works by compressing some gas. The gas gets warm, you dissipate the heat away, and then you let the gas expand, and it gets cold. And you also do this here, but at some point you have problems to get the necessary cooling power to go to 4 Kelvin. You use this mechanical compressor. The mechanical immersionness is simply too much to provide this, efficient cooling. So what you use instead, use just some helium gas inside the tube. And and for this compressor, for this piston, you don't use a mechanical piston, you use actually a shock wave of helium, which just travels through this material. And so you have some kind of compressed area of gas, which then acts actually as this piston, which then actually allows you to cool, to operate this as a Stirling cooler. And you do this at the end by basically applying a high pressure of helium here, and the next second you apply a low pressure of helium here. So basically you always change the pressure here, which then will stimulate this sound wave to travel through this pulse tube, and then at the end you get the cooling. It's a bit more product. Yeah, this is actually also why you typically hear a very typical sound in your labs. I'm not sure I have sound here. I was expecting to use my laptop here actually.
Fine.
Yeah, I'm fine, okay. So this is a funny video from IBM actually.
Welcome to Sounds of IBM. This is the first IBM Q Computation Center, where the commercial
Right, so here you can see the pulse tube. Here's the coax cable, some filters. Yeah, and this is a typical sound which you just hear in all these labs nowadays. But luckily, we also have sound insulation, and it's not so loud as in this IBM lab, in our lab actually. And of course, once you have set it up, you can just leave the lab and go back to your desk, or even measure from at home, because everything is of course computer controlled.
Can I ask a question?
Yes.
Can we think about the changing pressure?
Yeah.
As liquefying and non-liquefying, back and forth? Or it's a different state when it's in the highest pressure?
I think you can better compare it to this like Stirling cooler. You have some gas, you compress it with a piston, it gets warm, you let the heat dissipate away, and then you just expand it again and it gets cold. And this is how you use this.
So you could do this with any gas?
Well, I guess you could, but helium is typically very efficient because it's a small mass, which currently is an advantage.
So the principle is completely different from the fact that liquid helium is.
Yes. No, it has nothing to do with liquid helium. There's no liquid helium in the Stirling cooler and this pulse tube, except of course in the mixing chamber. Okay. Okay, so yeah, and of course you have this sound wave which travels through this pulse tube, and this is just what your point which you already raised. This can generate mechanical noise, mechanical vibrations. And in the next lecture you will actually see that you can even excite the qubit. The qubit is actually excited regularly with at the frequency of this pulse tube. So qubits coupled to this sound waves via the TLS actually. And this is just another source of noise mediated by TLS. Okay, so now we didn't talk about what's actually saw in these resonators. So, okay, imagine now you have this coplanar resonator here, and you look at the cross-section of these films here. So, as I told you, if you have some qubit electrode, you always have some amorphous metal oxide. And this, of course, then, as it's amorphous, again contains these atomic tunneling systems. Also, this is an interface here which is exposed to atmosphere, right? So you can expect that you have some adsorbates coming from your environment. Like, for example, hydrogen or oxygen can just separate some binding bonds here. And you always can have these molecules because typically they just appear from the dissociation of the water, the moisture in the atmosphere. So I told you that you have, of course, to structure this film somehow, for which you use photoresist or some chemicals. So this means that any kind of contamination that left from your processing chemicals can also generate problems here. And as I said, the photoresist is an amorphous material, which would likely, if you leave it and not completely wash it away, generate some local defects here. Any kind of other contamination, of course, can be a problem. Like if you cough on your sample, you can already have a variety of things lying there. Hopefully not so much anymore coronavirus. And also there's a new model of how TLS can be formed, which is by trapped quasi-particles. Here the idea is that you have maybe some change of the sogenannte order parameter or the binding energy you wish. And this allows some electrons to trap here in a certain position, and they can leave the trap or just tunnel between two traps, and then of course you have again charge noise. So these are all possible models of TLS, and as I told you, we are not completely sure what we are dealing with mostly. I mean, we know these sonic atoms are there, and everything here is very reasonable to assume it's also there, but we cannot say which is the largest problem here. And here's just some possible models how these defects can be formed. As I already told you, we have these hydrogen, which can separate some bonds here, coming atoms, of course, trapped quasi-particles. I'm sure Lara Faoro will talk about this in the next week in more detail. And yeah, basically, many things can go wrong here. So it's actually important to remember for the remainder of this lecture that the coupling between the TLS and such a quantum device occurs by, of course, the electric data moment of the defect. So the effective coupling strength between the TLS and the resonator or qubit in this case will just be the product of the data moment times the electric field driven by this oscillation here at the position of this TLS. And you will also see later that these electric fields here are very much concentrated at these edges of these films here, which is why TLS at these edges here are the most strongly coupled and most strongly interfering with your resonator, with your device. So if you have now such a resonator, you will see, of course, TLS showing up in several ways. One is that the quality factor depends on the power which you have inside your resonator. You can drive it high or low amplitude, change the power. We see that if you drive very strongly, you have a smaller loss, higher Q factor. And this is already one typical TLS effect. And it's easy to explain because, well, the TLS, which actually lower the quality factor, must be resonant TLS. These must be the ones at the same frequency as the resonator itself, because otherwise energy conservation is somehow not working. So this means that if you have such a resonator with some oscillating field, you can basically do Rabi oscillations. You see, Rabi can drive these TLS. So basically, the TLS can absorb a photon from this resonant field here and get excited. And of course, it can also get stimulated. It can also fall back in a stimulated way. So the Rabi frequency then is just given by the product of this again data moment times electric field strength, like the typical coupling strength of the TLS. And this means that if you drive harder, you will actually have a very fast Rabi oscillation. And at some point, this Rabi oscillation will be faster than this decay rate here. And if this occurs, then this means that this decay rate doesn't really matter anymore compared to this fast excitation. So you have basically generated a saturated TLS. So basically the TLS is like 50-50, and it's both excited and ground state. Yeah, and accordingly, you can then model these kinds of loss rate dependencies using this standard formula here, where the power now is just basically given here by the square of the Rabi frequency, which you just have to compare to these decay rates here in order to get some factor here, which then leads to this S-shaped curve. Actually, it turns, okay, it's not so important. Actually, when people do these experiments, they already find that this equation does not really hold. This is actually the prediction of the standard tunneling model. And they have already told you it neglects the interactions between defects. But this can be kind of fixed by taking into account these interactions, which is probably something also Laura will talk about. So basically, you can just add some factor here, which uses the filling factor, which then can also tell you about the interaction strength between these defects. Yeah, this is actually called the generalized tunneling model. Okay, yeah, also you'll see some effects of TLS when you change the temperature of your resonator. Here the mechanism is basically the same. At high temperature you get smaller losses. And why you do this? Because with high temperature you can excite the TLS thermally, and then once you excite them very strongly in a thermal way, they again don't really care about the phonons coming from the resonator. They will have the same probability emit a photon and absorb it. So that's why the TLS loss at high temperatures is basically approaching zero. Yeah, and this is actually called thermal saturation. Simply you generate a 50-50 population difference by providing enough thermal energy. It's actually surprising that the loss is reduced at higher temperatures. This is something you would not typically expect from, for example, for many devices, many things. Typically at small temperatures, losses gets reduced because you avoid these modes. Yeah, this is just another example how you can then measure this, and also another effect. This is the resonance frequency change of a resonator. Actually, the resonance frequency also depends on temperature, as you can see here. So there's a small shift of the resonance frequency, the relative decrease of the resonance frequency at a certain temperature range. At small temperatures, the TLS play a role. And you can then also, for example, make this effect stronger or weaker by changing the distance between this inner conductor here and the ground plane. This is just this parameter here showing the colors. If you use a large distance here between these two electrodes, you have actually not so much effect from the TLS. And this is just another demonstration that it matters how much electric field you have at the position of the TLS. This TLS talks to the electric field, and of course electric field will be much more confined in a very narrow gap here compared to a very wide gap. And this is actually already one design principle. If you want to make a good superconducting quantum grid, you should make sure that you have, that you avoid small distances where you have strongly confined electric fields, because you can be sure that all TLS here will be very strongly coupled to the device. This is another nice experiment from the Maryland group, who actually were able to also detect signatures of individual TLS using a lumped element superconducting resonators. So the trick here was to just make a LC resonator, but use actually 4 capacitors in such a bridge configuration. And this now allows you to put a voltage here versus ground here, which will just bias the dielectrics here. So some electric field will be confined in this dielectrics here, but since it's connected here at the center of the resonator, it doesn't really affect this oscillatory mode here, which basically just goes this way. And this is how they made it. This is the inductor. It's just a thin superconducting metal foam here. Here you see some overlap capacitors using some dielectric between the plates. And here you connect the voltage source, and here is ground. And what you then do is you just measure the resonance curve of these resonators. So you basically, this is now the resonance curve. So the dark means you have the minimum of the resonance curve, and the brighter colors just means it's basically one unique transmission. So here you see the resonance curve, and you see it's not really stable. if you now change the electric field bias, you see actually many of these kind of brighter lines here and somehow crossings. And these are actually avoided lower crossings where you drive individual TLS through resonance with your electrical resonator. So you can also fit these, and then you see, in fact, all these individual hyperbolas, each stemming from one individual TLS, being located in these dielectrics here, and then absorbing the energy from this AC electric field here at resonance. And of course, as I told you, when you have field bias, you can change the asymmetry energy of this TLS, and this, this at the end generates these hyperbolas.
Why do you need 4 transistors for that?
Well, if you have just a single capacitor and you have a superconducting inductor, you will not be able to put a voltage there because it will be shorted by the superconductor. If you have yeah, you cannot put a voltage there, so the voltage will just be zero because it is superconducting. Also, 2 I think is not enough. I mean, probably not. Yeah, okay, you could maybe use 2 if you put minus here maybe and plus here, yeah? But then you don't bias this one. I'm not sure. And of course, it's not good to connect something not in the center here, because only in the center the current is 0, so here you can connect anything and it should not affect so much. Should not affect so much the quality factor of your resonator. Yeah, you can focus on these hyperbolas here and really see, okay, these are really avoided lower crossings. You know, avoided lower crossings occur when you have 2 quantum systems which are coherently coupled. Then, and you see this here. Here you would expect a horizontal line here, but then the TLS comes basically through resonance, and at the point where both have the same energy, they have the level repulsion, and this shows us as these anti-crossings here in both situations, in both places, and you can use this to fit basically now the TLS properties. For example, the electric dipole moment you can fit, and also the lifetimes, just by looking at the width of these traces. Yeah, and also you'll find again typical electric dipole moments. So 5 devias are actually 1 electron angstrom, so it's just this electron angstrom magnitude which you expect to have from this TLS. Yeah, this experiment completed at some point in Karlsruhe. So we also just used some superconducting resonator here, and to cover it strongly to some defects, we put some overlap capacitor at the end here. So here the open emphasis lambda half resonator is just seeing some thin film of amorphous dielectric, in this case of muon oxide. So you have strong electric fields here, and then if you measure this, you see that actually this is a very noisy resonator compared to one which does not have this amorphous dielectric here. So, and this again just shows you all these fluctuations of these TLS as they just in time randomly change the state due to this interaction with the thermal fluctuators, as I have explained in the beginning. Exactly this mechanism here. So here you can now see actually that the resonator not only changes its quality factor as a function of time, depending on the vicinity here, but also the frequency is changed. It's kind of pushed away here because some TLS decided to come closer to the resonator. Yeah, and basically then these resonators are a nice tool to already study materials and to maybe try to find ways how to use better materials which have less TLS. And typically experiments which you do is like shown here. You can make resonators over different dielectrics, and see here for example again that silicon nitride is a bit better. The smaller loss at low photon powers. Also you can of course change the deposition condition and see that maybe, okay, molecular beam epitaxy is much better than sputtering, which is of course clear because NVE of course build the material layer by layer in a much more controlled way than just by sputtering it. And yeah, you can also see that if you are able somehow to remove the surface oxide, again you will have a much higher quality factor as if you have this native surface on oxide on top. But actually it's of course typically not so easy to remove the oxide, because once you removed it, you must keep it in vacuum, otherwise you will have again the oxidation. Okay, yeah, this brings me nicely in time to the end of my first lecture, and I showed you some basics about TLS basically. So the key points to take away is that The coupling between the individual defect and your device is given by the electric field. The device generates at the position of the defect. This is actually just some matrix element, which is symmetry of the TLS. And that there's many possible ways how we can get problems from TLS, and we're not really sure what actually they are. But we have now at least quantum devices by which we can look even into individual defects, even with the resonator, if you design it properly. Okay, yeah, and this brings me to the end. Next lecture, we will see what we can do with superconducting quantum bits. So here about the basics, of course, the decoherence mechanisms, especially considering TLS, and also some words about the state of the art of the superconducting quantum community. So yeah, with that, I would like to thank you very much for your attention. I hope it was a bit interesting. And then I'll see you back in Tuesday for the next lecture.
Questions to the lecturer about lectures? Very
Enjoy the weekend.
Thank you.